This video is going to cover our first lesson on modeling with functions, Unit 4. The first thing I want you to do is open up your packet to page 2 and examine pages 2 and 3. On page 2, you have a list of function family names and you have a set of parent functions. What I'd like you to do is to please pause the video and match as many functions as you can to their parent graph. At this point, you should have tried it on your own, and hopefully the first thing you notice is that graph F is linear. It's a line. When we look at exponential functions and we look at our choices, we see that graph D is an exponential growth. Graph C is quadratic. It is a parabola. I might skip polynomial for a moment because I'm not quite sure, and I'm going to go to some of the ones I'm 100% sure about. I am 100% sure that graph I is trigonometric. I am also 100% sure that graph G is an absolute value function. So now we have polynomial, rational, logarithmic, and radical. I notice that graph H and graph A kind of look similar. I look at graph E and I see it has both a vertical asymptote and a horizontal asymptote, which makes it a rational function. It's actually the function 1 over x that you'll remember from the beginning of our semester together. Okay, so now I'm down to polynomial, logarithmic, and radical. So I'm pretty sure that B is the polynomial function. It looks like it's even degree because the arrows go in the same direction. Possibly it's an even degree positive leading coefficient. So I'm going to mark the polynomial as graph B. So I'm left with graph A and graph H, and they're pretty similar. And I want to figure out which one's the logarithm and which one's the radical. I remember that radical functions are functions like y equals the square root of x. If I start to substitute numbers into the square root of x, the square root of 0 is 0, and the square root of 1 is 1. And I notice that graph A has a point at 0, 0, and 1, 1. So it's a pretty good candidate for radical. When I look at graph H and I look at it more carefully, I notice it's got this vertical asymptote here at x equals 0. And radical functions don't have that property, so A is going to be the radical function. That must mean that graph H is the logarithmic function. As a reminder, logarithms and exponentials are inverse functions. And if we look at this, if I recopy graph D onto graph H, I do see like this point 1, 0 becomes 0, 1. The graph curves up like this. The asymptote comes down. They do look like they are reflected over the line y equals x. They are inverse functions, and graph H is the logarithmic function. Okay, go ahead and turn to page 3. Now, page 3 has a set of parent functions, or just functions with, no numbers, and I need to identify what family they are. So obviously, number 1 has got an absolute value. Pause the video, work on your own, then come check. We've got absolute value. It's got absolute values around it. And I'm using page 2 as a word bank, by the way. Obviously, these are our family of trig functions. Mx plus b from algebra 1, these are our linear functions. This is obviously logarithmic. Graph 5, standard form of a quadratic. 1 over x, as we said on the previous page, that's our parent function for a rational function. A times b to the x, that should look familiar from first semester. We spent a lot of time writing equations in that form. That is exponential. And number 9, I'm going to skip number 8 for now. That's a little scary. Number 9, when I look at it, this n, it's the nth root. So, for example, if n was 2, it would be a square root. If n was 3, that would be a cube root, and so on and so forth. So let's go back up to tricky number 8. When I look at tricky number 8, I see it's got an as like a coefficient, and then I've got an exponent here, and then it's going down, my exponent's going down by 1, until there is no variable at all at the end. It's almost like this is a constant. And what we have here is we have a polynomial function. So for example, we could start a polynomial function like y equals, I'm just going to pick some numbers. We could have 10x to the 5th, and then another coefficient like 7x to the 4th, and I'm just going to fill this in, making stuff up. But you'll notice that my powers are going down. 5, 4, 3. We'll make this 4x squared plus 5x, and we'll give it a constant of 10 because, I don't know, seems like a good idea. But this follows our format where an is the leading coefficient, a sub n minus 1 is the coefficient of the term with the power n minus 1, a sub n minus 2 is the coefficient of the term with the power n minus 2, and so on until we get down to a sub 0, because as we remember, if I had like 10x to the 0, x to the 0 is just 1, 1 times 10, whoops, 1 times 10 is 10. So we've matched up all of our parent functions with their graphs and their equations. Now we're going to take a look at some different scenarios and determine which parent function fits best. You can use the function types more than once or not at all. Take a second, pause the video, and familiar yourself with these 7 scenarios. If you can, graph a little, what you think this would look like, and maybe that can help you determine what function type. Again, pause the video and at least read it and hopefully try it on your own. Okay, letter A says, the kicker on a football team kicks a field goal. How does the height of the football change over time? So if you can imagine, I have my little person here, and he's going to kick the football, woo, and maybe it goes through the field goal, maybe it doesn't, I don't know. But you can see that here we've got a parabola, so I'm going to say that this is going to model a quadratic function. B says the number of hours of daylight in Rockville changes over time. So like in the winter, maybe there's not very much sunlight, daylight, but then as we get, towards the summer, the amount of daylight peaks, and as we get back towards winter, the hours of daylight decreases, and then when we pass that day in December where it seems like it's dark all day, it gets more daylight again, and you can see we are starting to model a sine or cosine function. So this is trigonometric. Each week you deposit your paycheck from your part-time job into your savings account. How does the balance of your account change over time? There's actually 2 scenarios that could happen here. The one that's going to seem most realistic is that you're going to have a linear function because you're depositing your paycheck every month and it's just going up. So it is possible that you have a linear function. Now, if you're investing wisely, and hopefully this is what's happening, you have an exponential function because maybe you're getting interest, but it really does depend on the scenario. So I'm going to put both. Enrollment in Montgomery County Public Schools is 1.6% higher this year than last year. If this growth rate continues, how will enrollment change over time? So percentage, it immediately tells me that this is going to be an exponential, probably an exponential growth, where I'm given a growth rate. I can't spell. I think that's right. A group of people are buying a gift for a friend. The amount each person will pay is determined by dividing the total cost by the number of people. Well, the cost isn't changing, but the number of people purchasing the gift is changing. So what we have here is we have a rational function. This is actually the first problem we looked at. Someone was buying a gift for a quinceañera, I think, and how much everyone was going to have to contribute. I know you all got triggered when you read this problem. It's a Ferris wheel problem. It's trigonometric. And the last one, a plumber charges a call-out fee plus $55 an hour. I'll be straight with you. I just had to hire a plumber. If you can get that price, I would question his work. But this is going to be a linear function. This is actually like our y-intercept point. Whoops. Our y-intercept point. And this is the slope. The last thing we're going to look at today is we are going to look at transformations of functions using some point notation. Now, what I want you to do is I want you to really notice as you look at these sets of points, what is happening to both the x values and the y values. So the directions say fill in the empty boxes using geometric and function notation to describe the transformation from the pre-image, the parent graph, represented by each set of image points. Name the function family name for each pre-image. So I see first off, I've got x squared here, which tells me that this is quadratic. I want to remind you that parabola is a shape. Quadratic is the family. All right, now I see, and this one, the first one's done for me, my function is I'm adding 2 to each one. And one of the ways I can see this in the points is I notice, I'm going to use a pen to just highlight, I'm looking at these x values here, and I'm noticing that the x values don't change. And I'm noticing that the y values 4 to 6, 1 to 3, and this 0 is definitely a clue that it goes to 2. Because it goes 0, 2, I know I'm not multiplying, because 0 times anything would just be 0. But it's going 0 to 2, and so that agrees with the fact that this function is x plus 2. So let's look at image 2. Image 2, again, I notice all the x values are the same, so I don't have to worry about x. I'm not gonna write this xy because honestly, I just don't have enough space. So this is gonna go, I know the x stays. Now when I look at the y's, I notice that this 0.00 is still 0, 0. So I know that this was probably a multiplication pattern. So when I look at 4 and it goes to 10, 4 times 2 is 10. 1 times 2 is 2. Yep, this is multiplying by 2. And so the function is just going to be 2x squared. When we look at image 3, again, I'm going to start by looking at these x values. And the first thing I notice is that they've all shifted a little bit. -2 became -3, -1 became -2, 0 became -1, and so on. So I know that the x values have all subtracted by 1. Okay. The y values have stayed the same. When I go to write the function, I have to be a little careful. So originally my vertex was at 0, 0. Now my vertex is at -1, 0. So let's make a fast graph to just discuss this. So I've got -1, 0, and then I've got 0, 1, and I've got -2, 1, and the graph goes like this. And we can see that this graph has moved to the left. So my function is going to be x plus, oh wait, and there should be a plus up here also, x plus 1 squared. And now here's what I recommend you do. What you have to do is pick a point and make sure you get the right thing. So I'm going to pick 1, 4. And if I do 1 plus 1 squared, do I get 4? Yes. Okay, to check my point, I'm going to say, okay, if I take 1, 4 and I substitute it back into the point 1 plus 1 comma 2, or sorry, comma 4, do I get the original point 1, 2, 4? Yep, it's the same point. No, I was right the first time, guys. I'm sorry. It's late. This should be minus. Yep, that should be minus. I apologize. Okay, now we've got an exponential function, 2 to the power of x. All right, so again, I'm going to look at the x values. Nothing's changed. So I know that I'm going to x. But I look at the y values, and I see that the y values, I've multiplied them all by 4. Yeah, because 1/4. So this is going to become 4y. And it's just going to be f1 is going to be 4 times 2 to the x. All right. So now image 2, the x's are still the same, but all the y values are negative. So I've got x, -y. And so my function is just going to be f2 of x equals -1 times 2 to the x. Now for image 3, I see that I've moved again to the left. So I'm going to have x minus 1, but then the y values stay the same. So my function to move to the left is going to be 2, and then up in the exponent, x plus 1. All right, number 3 is an absolute, oh, there was a little spot here for function family name. I didn't even see that. That was so silly of me. So this is an absolute value. I examine the x values. They're the same. That's nice. The y values, though, oh, that 0, 0 is a key. It's got to be a multiplication pattern. I'm definitely multiplying by -2 because 2 times -2 would be -4. So f2 of x will be -2 times the absolute value of x. All right, image 2, I'm moving all the x values a lot. I'm moving them to the right 4. So in the absolute value sign, I'm just going to make a note. It needs to be x minus 4. But the y values stay the same. So just to be clear, because I apologize, I thought I messed up, but then I didn't mess up on number 1. When we move to the left and the right, the geometric notation is going to be common sense. But then we know from our experience that the function notation is whatever happens in the argument is the opposite. All right, so same thing here. Y values don't change, but the x values, I've moved them all backwards 3. So f3 is going to be the absolute value of x plus 3. And again, like when I substitute in -5 here, -5 plus 3 is -2, and then the absolute value of -2 is 2. Okay, at this point, pause the video and try the 2 sets of problems on page 6. Okay, you should have identified number 4 as trig, or you could even say sine. We notice that it's kind of nice. The x values don't change for 1 and 2. Or sorry, for 1 and 3. The y values don't change for number 2. Here, all the y values appear to be adding by 2 because I'm going 0 to 2, 1 to 3. So y plus 2. And then this becomes sine x plus 2. Now, when I look at image 2, I notice that this is kind of my key here, this pi. And over here we've got pi over 2. And then here we've got 2 pi and then to pi. So what's happening is we are dividing the x's by 2. Now here we got to be careful again. Something's happening on the x's. So what has to happen if I substitute these, avalanche, earthquake. If I substitute these x values, then I have to get 1 back. So what I'm going to need to do is I'm going to have to say f of 2 of x. I need to double all these x values because in order to get 0, this pi over 2 has to become pi. To get 1, this pi over 4 has to become pi over 2. So I need to double all of these x values in order to get back these y values. Now the last one, I've noticed, again, the 0 is always a key, that I got a multiplication pattern going here. And I've got 1, -2, which tells me that I am multiplying by -2. That's just going to be a dilation. Alrighty, 1 left. Here we've got a radical function. If you said square root, that's great. I would take square root, but really the family name is radical. I'm going to look and I notice immediately I'm happy. I like number 1 a lot because x's don't change. Y's are just being divided by 2. So my function is going to be 1/2 the square root of x. Now here I've got the 0, 0 stays 0, 0. So whatever's happening is multiplying. I noticed that the y values are still 1, 2, 3, 4, but now the x values are all they've all been divided by 2. Now, when I write my function, I have to be able to take the square root and get 1. So it's going to have to be the square root of 2x, because if I multiply 1/2, 2 times 1/2, that will give me 1. Yo, some of us are trying to record a video. Stop screaming at the television. All right, and the last one, image 3. The y values stay the same again, but these x values, what is going on? I've got a 0, and that is, could it just be plus 3? Yes, it's just plus 3. So y plus 3. And then we've got f of 3 is going to be the square root of x minus 3. Because if I'm substituting in this 3, it's going to have to be 3 minus 3 to get the square root of 0 to give us 0. Hope that helps. Homework, I want to say 7 and 8, but check your brand new calendar that you picked up today.